All right, kids, sorry this has taken so long, but everything that I've touched today technologically has just gone crazy, and it's been a struggle, and this is why this is so late getting out, but we'll make it happen. So, so this is going to kind of wrap up a whole bunch of different things. So let's say that we have a reaction uh, of nitrogen plus 3 hydrogens, and those are gases, and we're going to yield 2 moles of ammonia gas. So this is what's known as the Arbor process. It's one of the most important reactions that took place because it allows us to produce ammonia, which is used as a fertilizer. So this is one of the most important processes because once fertilizer became cheap and readily available, then that greatly increased the production of wheat, corn, soybeans, okay, a whole bunch of crops across the world. So this is a very important equation in terms of historical perspective. So by this point, we should be able to calculate a couple of different things. So if you go through and let's say, okay, we want to calculate delta S naught. So this is going to be this change in entropy. So without boring you, if you go through and you look up and you find your change in your entropy for NH3, and then you add your NH2 and subtract that, and your hydrogen and subtract that, you get, wait for it, negative 198 joules per mole Kelvin. Okay? So now let's look at why this might be a negative value. First off, you have 4 moles of gaseous reactant, and you only have 2 moles of gaseous product. So based upon that, we've got to figure that this entropy is going to decrease just based upon the fact that you're going from 4 moles down to 2. And so generally, especially when you decrease that by 2 moles, this is why that delta S is going to be a negative value. Now, if you go through and you calculate delta H naught, you get negative 92.38 kilojoules per mole Kelvin. Now, notice here you've got a couple of things that are important. Both of these are negative. So your enthalpy term is driving it towards spontaneity, and your delta S, the change in entropy, is driving it away from spontaneity. So right away we know this is going to be a temperature-dependent reaction. They're both negatives, so the temperature has to be below a certain point, okay, and we can find that, okay? So at this point, you should be able to look at this, and just by virtue of the fact that you have a delta S, a negative delta S, and you have a negative delta H, right away you realize, oh, this is temperature dependent. Your entropy is driving it away, your enthalpy is driving it towards. So right away, as soon as the other thing that you can look at logically, as soon as I saw the negative delta S, I knew that my delta H, even before I calculated it, had to be a negative value. Because if this was a positive delta H, it's not, but let's play the what if game. If that had been a positive delta H, then this reaction would never take place. No matter what we did, we could never get this reaction to take place. So we wouldn't even be talking about this reaction because there's no way to make it happen, because you'd have a negative delta H, or negative delta S and a positive delta H. You'd have both things working against it, and you could never get a negative delta G. Now, let's say that we want to calculate delta S for the surroundings. Okay, now remember, delta S for the surroundings is negative delta H naught divided by temperature, which in this case would be negative 92.38 divided by 298 Kelvin, assuming that we're running it at room temperature. And now, keep in mind, this is going to be a negative of this negative, so this in effect makes this a positive value, okay? So delta S for the surroundings, then if you do the math, you get 310 joules per mole Kelvin. Now, hopefully this makes sense, because now when you look at this, hold on. Oh, that's kilojoules. Okay, I was going, whoa, my math is way off. That's because kilojoules. I forgot that I changed that into joules. My bad. I had a momentary panic. If I had those today, don't flip out. It's been a really, really stressful day. Just go with it. So it's like, that can't be right. It is because this is in joules. That's why you pay attention to the units. All right. So delta S for the surroundings is going to be a positive value. Delta S for, and this is for the system, right? It's going to be a negative value. So the surroundings are going to increase in entropy, and hopefully that makes sense. The delta S for the surroundings is going to increase in entropy because of the fact that it's an exothermic reaction. This reaction is giving off energy. So the area around where this reaction is taking place, okay, so the reaction is taking place in some vessel, right? It's an exothermic reaction, so it's giving off energy. So the area around this thing is going to be gaining this energy, and it is going to be increasing in entropy. So the surroundings have an increase in entropy based upon delta H. Now, here's the anomaly. Notice delta S of the surroundings has nothing to do with the system in terms of a calculation. The only thing that determines delta S for the surroundings is this negative delta H over T. Do not, I repeat, do not forget the significance of that negative. So this is why we have a negative of a negative. We end up with a positive value. That's why that works. Now, let's calculate delta S of the universe. Okay? Now, that's delta S of the system plus delta S for the surroundings. Now, before I do any calculations at all, I know that my delta S has to be a positive value. Okay, and I know it has to be a positive value because this reaction takes place. And spontaneous reactions, you have a positive delta S for the universe because you're increasing the entropy of the universe. So if you go through here and you take the delta S for the system, negative 198 joules per mole Kelvin, add that to the delta S for the system, 310 joules per mole Kelvin. And if you do this math, you get a positive 112 joules per mole Kelvin. And that matches with what we think should happen because of the fact that this reaction is spontaneous. Therefore, it is increasing the entropy of the universe. And there we go. All right. So we're good with this. Now, if you wanted to, and if you go through and you wanted to calculate your delta G, oddly enough, in this case we're not going to because we know the delta G is going to be a negative value. And we know that it's going to have a negative value because of the fact that the reaction is going to be spontaneous. Okay, now let me work through some other problems in terms of how sometimes this gets phrased. So let's say you got C3H8, otherwise known as propane, and kind of important going into the growing season, especially amongst being isolated. That's a gas, and that's a gas. And we're going to produce carbon dioxide and 4H2O, and we're going to make that liquid water. And that's a gas, okay? So what can be given on this problem is that you might be given something like this, where you'd say, okay, predict whether delta G is more or less negative than delta H, okay? And then we're going to, now, so let's talk about this. So let's just look through this. I've got 6 moles of gaseous reactant. Because I'm talking about liquid water, I only have 3 moles of gaseous product. So since I'm going from 6 to 3, I've got to figure that my delta S value, once I go through and calculate that, is going to be a negative number because of the fact that I'm going from 6 moles down to 3. So in this situation, you don't actually have to do the calculation if you can just look and see what's happening. So in this situation, you look at delta G equaling delta H minus T delta S. So there's a couple of things that are important. Number one, since we used this to cook with, it's an exothermic reaction. So I know I'm going to have a negative delta H, okay, minus T. Now, I know my delta S is going to be a negative number, okay, because of the fact that I'm going from 6 moles down to 3 moles. So if you look at what's going to happen then, I'm going to have this negative delta H. If you do the math, it's negative 2,200 kilojoules, minus T times this negative delta S. So that means this is going to be positive, so I'm going to add this value. So what this means is because of the fact that I'm being driven towards spontaneity from my enthalpy term, I'm being driven away from spontaneity with my entropy term, then I've got to figure that because of the fact that I've got this negative delta H and a negative delta S, I'm going to end up adding this, so this is a positive number. So my negative delta H, my enthalpy term, will be less, will be, because I'm adding this, my delta H will be less negative than my delta G. My delta H, I'm sorry, I screwed that up. Again, it's been a long day. My delta G is going to be less negative than my delta H because of the fact that I'm adding this positive number to it. And so since that gets added to it, delta G is going to be less negative than my negative delta H. Now, if this had been a negative, or if this had been a positive delta S, let's say it had been a positive delta S, then I'd subtract a negative value from that, and then my delta G would be more negative or bigger value than my delta H. Okay, that was a struggle. Okay. Oh, all right. So here's the other way that you can look at delta G. Delta equals delta G naught plus RT times the natural log of Q. Now, so if you look at this in terms of this reaction that we talked about, the N2 plus 3H2 yielding 2NH3, okay? So we figured out the delta G value was, I lost that somewhere. We'll find it again. So because of the fact that we know this reaction is going to take place, and these are going to be gases, the Q value here is going to be based upon, I have no idea what I just did. But let's go back. Wow. Okay, that got weird really quickly. I have no idea what happened. Just this random, oh, I must have hit the magnify box in the corner. Okay. All right. So because of the fact, let's continue with our story. Because of the fact that these are going to be gases, this Q is going to be based upon pressure. Now, again, this is old school. So your Q value is going to be your pressure of your NH3, okay, because that's going to be my product, but that's going to get squared. And then I'm going to divide that by my N2, and then my H2, and that's going to get cubed. So this is old school. This is the same system we use with QSP, KSP. You cube it, you square it, whatever is in front of that. Now, so here's what I want to look at. If I want to figure out a point where we're going to be at equilibrium. So at equilibrium, delta G is going to equal 0. And that's going to equal delta G naught plus RT times the natural log of Q. Now, but here's where the magic happens. Because we're going to figure out what's going to happen at equilibrium, instead of Q, we're going to put K. Now, let's do a little bit of magic here. So I'm going to subtract this delta G over. So I'm going to have negative delta G naught equals RT times the natural log of K. Then if I solve for K, and then I'm going to get e to the negative delta G naught over RT. So again, this should be old school and potentially an aha moment and go, oh, this is kind of cool. So remember, this is a K value. This is going to be at equilibrium. So if you look at what's going to happen, if you have this negative sign, so if you have a negative of a negative delta G, that means this becomes positive. You're raising e to a positive value. That's going to create a big K value, which means it's favored in the forward direction. If you have a positive delta G, okay, which means it's non-spontaneous, if that's the case, then you're going to take e to a negative positive delta G, if that makes sense, over RT, and you're going to get a really, really small value of K. So this hopefully goes, all right, this is how K relates even to delta G and this whole idea of equilibrium. So now that we know how to calculate delta G naught, so we could come up here, we could go through the math, we could find the delta G naught. That delta G naught is going to be a negative of a negative value. We can figure out what that value is. So here's kind of the summary. If you've got a negative delta G, that means your reaction is going to be spontaneous, which is kind of cool, right? So we're going to have a spontaneous reaction. And we're going to have a K value much bigger than 1, so we're favored in the forward direction. If delta G naught equals 0, guess what? K equals 1. The system's at equilibrium. If delta G naught equals a positive number, guess what? We're not spontaneous. And K is going to be less than 1. So those are the three options that you can come up with. Okay? And again, hopefully this kind of all becomes old hat. So now here's how this would actually play out. So for this reaction, this Arbor process, when you look at, I'll rewrite that so we're all on the same page. So you got N2 plus 3H2 yielding to NH3. Delta G naught is equal to a negative 33 kilojoules per mole. Okay? That's a horrible 3. 33 kilojoules per mole. Okay? So there's my delta G naught. Notice this is in kilojoules. So if I want to find out the value of delta G, and let's say that we're running this with these same pressures of N2 is 1 atmosphere, H2 is going to be 3 atmospheres, and NH3 is going to be at a half of an atmosphere. Okay? And I want to figure out what this is going to be. So here's what I've got. I've got my delta G equaling delta G naught plus RT times the natural log of Q, because I don't know what the reaction is going to do. So here's what you have to be careful of, okay? And Reimer, listen to me. So if I'm going to go with this delta G naught, I'm going to put that as negative 33,000 joules per mole. And here's the reason why I'm going to do that. Because of the fact that when I do this, okay, this R is going to be 8.314 joules per mole Kelvin, okay? So this is why this has to be in joules. Now, we're going to run this at room temperature, so that's 25 plus 273, and you get 293 Kelvin. So that's going to be my temperature. And then I'm going to take I run out of room. And then I'm going to take the natural log of my products, which is going to be my NH3 concentration, which is going to be 0.50, but that's going to get squared. and then I'm going to divide that by my N2 and 3H2. So my N2 concentration is 1 atmosphere. And then my H2 concentration is going to be 3 atmospheres. But my H2 is going to get cubed because of that coefficient. So that's going to get cubed. So I apologize for running out of room, but imagine this whole thing is in here. Now, so if you do this, you get, and I remember that you get like negative 3,206, something like that, joules. Okay, about that. Here's the main point. You're going to get a negative value. So what that means is that because this delta G is a negative value, that means under these pressures, this thing is going to be spontaneous, and you're going to end up with a spontaneous reaction. So, and the forward reaction is favored because you've got a negative delta G. Now, here's the other thing that's cool. You can also, when we talked about Hess's law, and you can manipulate things and you could use them with enthalpy, you can also use them for your Gibbs free energy as well. So Hess's law isn't just relegated to enthalpy. You can use it for Gibbs free energy if you need to. Okay. All right. So I'm done. It's been a horribly long day. I apologize for this being so late and me being so tired, but it's just been a day. I will get this uploaded. I will get that last assignment and the answer key uploaded to you as well. And yeah, so that's the story. See you, kids.